Hi everyone, in this video I covered a Null-text Inversion paper from CPR23 for editing the real images that is quite popular. At the time that I'm recording, it has 743 citations, and yeah, let's just see what it brings to us. In DDIM that I have a YouTube video explaining what it does, remember that we have a XT noisy image. We predict the X0 in a single step and then add noise with less severity to reach XT-1, one step less noisy. And optionally, we have a random noise as element of stochasticity. And this random noise is defined by this equation that relies on hyperparameters alpha t and alpha t-1 that are coming from a predefined scheduler. But more importantly to us is this eta hyperparameter that controls how much random noise we want to add. Like if I define this eta to be 0, that simply means I have no element of stochasticity, and given a noisy image xt, I have a fixed deterministic path from xt to x0 without any randomness. And inspired by DDIM, we can define DDIM inversion that is exactly the same as before, but the difference that we don't have any randomness, or eta is 0. And in addition, we added with more severity so that we reach xt plus 1 instead of xt-1 given xt. And what is the point of it? Let's say I have this image of a flower. If I use DDIM inversion, then that means I have a deterministic path that by iteratively repeating it, I can reach a pure noise image. But what is cool now is that given this unique noise image, I can just apply DDIM with no stochasticity by setting eta to be 0 and reach the exact same image I initially had. All because I have a fixed deterministic path between this noisy image and the actual image and using the DDIM formula. But what is the gap that this paper tries to solve? The thing is, if you want to do this in practice, what you might do is to use this image with a text condition so that to change the text and do the image editing. You don't necessarily need to come up with a caption to describe this image, and what you can give it is something like clip cap, surprisingly from the same authors, to describe something like zoom photo of flowers. And unlike what I mentioned earlier, the denoiser should receive the noisy image xt in addition to the condition c as the input, and this c is in this case a text condition. And having our denoiser, which is a stable diffusion, we can apply DDIM inversion to reach this noisy image. But now the issue is that if you use DDIM, you'll see a different image with a different layout and a different style, but with the same semantic. And this is not good for us, especially for the case that we want to do image editing, because even without changing the text, we can't have a one-to-one mapping between our actual image and the noise image. And that's where this paper comes in to introduce null-text inversion to solve this issue. And as the application, you can combine this technique with prompt-to-prompt image editing, which I also have a YouTube video about it, to change the text and edit the image. Hopefully the problem definition makes sense, and now let's see what this paper brings to us. Before talking about the method they propose, I'd like to talk about classify free guidance and give you a very nice visualization of what it does and why it works. Let's say we have a text prompt like a corgi with flower crown, and we want to generate an image. If we use a stable diffusion without classify free guidance or CFG, we have this beautiful visualization from PhD paper from CPR 2024 that shows that at each diffusion denoising a step using DDIM formula, what is this one step x0 that we reach at each step, and they visualize it over denoising process. What you see here is that at the end you'll reach this generated image that clearly has some artifacts, and CFG is proposed to mitigate it. And the way it does is using this formula that is made of a summation of two terms. The first term focuses on denoising using xt and using the condition c, kind of like a regular denoising without any CFG whatsoever. And the second term is the difference of denoising one time seeing the text condition and the other time not seeing the condition, scaled by a hyperparameter w. And when I say it doesn't see the text condition, I mean use the same model but receiving empty string as the text prompt. And also note that this is happening only at inference time, and during training we have a dropout mechanism that sometimes the model sees the text condition, sometimes it doesn't, but that's not really important here in this video. What we really care here to understand how this CFG works is the difference inside this equation that we can denote it by delta t. If we visualize it, here you see on the second row the result of with receiving the text, on third row without it, and final row the difference between them, and the columns are different denoising steps. What is interesting here is that on a particular step, let's say t-1, you see that here is the result of one step denoising at t-1 while receiving the text condition. And what is interesting is that you can kind of see that there are some overall formation of how the dog looks like, and you see that the formation of its nose. But without the text condition, since the model doesn't know about the dog, it doesn't create the region for the nose, and therefore the difference would be an area where the nose is visible. Having this difference delta t, we added in diffusion denoising a step with the hyperparameter w to intensify the nose region of the dog. And note that how much we added by changing the scale hyperparameter w matters, because if we intensify it a bit, then we might still see the artifact, while if we intensify it much, then we have other issues like oversaturation as the nose area becomes extra visible and it is more than what it should be. And now coming back to our problem, when we initially have our input image z0 star, using DDIM inversion, we can reach z1 star and then z2 star and doing it over and over until we reach z capital T star. And note that this path is not linear and we can't do it in a single step, but it is something like a piecewise linear, meaning that if we do it in multiple steps like 50 as they usually do, then once the model receives z1 star and predicts some noise and then add it to reach z2 star and next step receive z2 star and predict another noise, we expect these two predicted noises to be equal, while in practice they are not. If they are exactly equal all the time, then that means we have a linear path from z0 star to z capital T star. But the thing is that there's a tiny bit of difference between them, and we do it in multiple steps like 50. And this tiny bit of difference doesn't produce any harm for the case of unconditional image generation, but remember for the case when we have a text prompt, we use CFG and we intensify the difference by a scale hyperparameter. And when we intensify the difference, we also intensify the difference between the two predicted noise, and that's where it becomes problematic. Like at first we reach zt-1 bar that is a bit different than the actual zt-1 star that we initially had in DDIM inversion, and as we go further this difference becomes bigger and bigger till we reach z0 bar that is semantically the same as the initial image, a baby wearing a blue shirt laying on a sofa, but these two images are not alike. And that's where this paper comes in. They have this idea called pivotal tuning that by calling all zi's on the middle, it just tries to minimize the difference by having an extra tuning step in the image editing process. But here is the risk. If I tune the model weights for this pivotal tuning purpose, then I change the weights that it has learned from billions of images, and now I'm modifying it from a single image that I have at inference time, and that is too risky, because the model has learned a good image prior, and we are at the risk of forgetting it. So what this paper suggests instead can be shown in this figure, that instead of tuning the weights of a diffusion model, here they denoted by DM, you can see the procedure of a classifier free guidances once again. But remember when I said we have an empty string for unconditional one? Well, that empty string goes to a clip model and produces an embedding vector, right? So they say, let's just use that embedding as the initialization point and tune the embedding vector at each denoising step by optimizing this pivotal tuning and make the z bar more similar to z star. So to simply put, when I have 50 DDIM steps, I have 50 null embeddings coming from an empty string, each initialized by a null text at each unique diffusion step, and we tune that embedding vector with the purpose of optimizing so-called pivots and make the z star and z bar as similar as possible. And to just show you exactly what I mean, let's just look at this pseudocode that others provided for this null-text inversion method, that we have to do it for each single image we want to edit at inference time. As the input, we have a source prompt C generated from clip model given the text prompt P and an input image I. And as the output, we want a noise vector z capital T, which is a unique noisy image for that particular image. And we have a set of embeddings that we want to optimize with the same number of DDIM steps, which is typically 50. Initially, we set the guidance scale to be 1. And remember from CFG formula that by setting W to be 1, we removed the second term and only kept the first term. And that means we don't have any CFG at all. And then we compute all the intermediate Z stars using DDIM inversion. Then we set the guidance scale to be 7.5, which is a typical value used for CFG, and you see it in almost all the works. And then we initialize ZT bar to be ZT star, and the embedding for that step to be an embedding generated by clip text model receive an empty string. And then at each denoising step of DDIM, which is a loop that it repeats 50 times typically, we have an optimization loop inside that we repeated n times, that they use 10 times. And inside of this optimization loop, all we do is a simple gradient step that each time the denoiser of diffusion model receives the ZT bar and the embedding and the text condition, and using CFG, it generates ZT minus 1, and we force that ZT minus 1 to be similar to the ZT minus 1 star that we initially had in the DDIM inversion, and we optimize the embedding value to make that happen. And once optimized, we go to the next denoising step and optimize another embedding. And that's the end. We want to return the unique noisy image ZT bar and set of embeddings we optimized. And having this embedding values, now we have a one-to-one mapping between the noisy image Z capital T bar and the actual image Z0 star. And then we can use the same technique of prompt-to-prompt tuning to edit the image. And the results are pretty good, although there are tiny bit of inconsistencies, like here you can see that initially the hoodie of a man doesn't have any marks on it, but sometimes unintentionally it creates one without explicitly giving it as a prompt. But I'm not sure really whether it is because of the null-text inversion or prompt-to-prompt editing method. And yeah, that's all I wanted you to know about this paper. If you enjoyed it, don't forget to like and subscribe. And until the next video, goodbye.